So Professor Uday Maitra is a professor at the Indian Institute of Science, the institute to which I belong to. Professor Maitra is a very renowned scientist in organic chemistry, and he has been associated, apart from his professional activity on science, he has been associated with such popular talks on science for a very long time, mainly through perhaps Indian Academy of Sciences. We are very, very privileged to get him today as one of our speakers. Professor Maitra is again, for his scientific activity, recipient of various awards and honors. And it's instructive to look at his webpage. So I would strongly recommend that our young friends look at the web pages of both the speakers today. They're very instructive. And Professor Maitra is a fellow of the Indian Academy of Sciences. And now I invite Professor Maitra for his talk.
Let me go to the first slide. So I would like to share with you some experiments which teach us certain principles of chemistry. Physics gets a lot of publicity in newspapers, in the media. Chemistry, unfortunately, does not have that sort of a status in the minds of the public. Chemistry is often associated with problems like gas leakage, pollution, and things like that. But I hope that by the end of the hour, I will be able to change your and others' perception about chemistry. But let me first of all define what we mean by chemistry. So chemistry, we will define for today's talk as being the process which makes and breaks bonds between atoms and molecules. So if there are no bond breaking or no bond making, there's no chemistry. Before I begin a formal presentation, I would like to remember these three great scientists because they were born, first two of them yesterday on 27th August, and the third one was born today. And every day of the year, something interesting has happened in the history of science, in the history of chemistry, physics, maths, and biology. So let us celebrate these three great gentlemen. First one, August 27. The first picture on the top left is Carl Bosch, who was born on this day in 1874. And he developed the commercial method, the so-called Haber-Bosch process, which I'm sure all the class 12 students would know, for producing ammonia. And he got the Nobel Prize in 1931. And if I'm not mistaken, Fritz Haber got the Nobel Prize in 1918. The second picture, also born on August 27 in 1913, is Martin Kamen, who discovered carbon-14 and developed radioactive tracer techniques in biochemistry. Again, a very, very useful techniques for studying a lot of biological and also non-biological reactions. And coming back to August 28, that is today, this gentleman, George Whipple, was born in 1878, and he worked on pernicious anemia and diabetes and got the Nobel Prize in Medicine, along with two other names. I will mention it in a minute, in 1934. And his work was indirectly on vitamin B12. Incidentally, vitamin B12 has, the 5 Nobel Prizes on direct and indirect studies of vitamin B1 came out. First one is George Whipple, George Minot, and William Murphy in 1934. Alexander Todd, who worked on the structure of vitamin B12, got the Nobel Prize in 1957. And Dorothy Hodgkin on the X-ray crystal structure studies on vitamin B12. So because of the importance of vitamin B12 and in the context of today, I thought I will show you the chemical structure. It is one of the most complex vitamin structures, and interestingly, the only one which contains cobalt in our body. We don't need much of it. We need about between 1 and 2 micrograms per day. And this is the only cobalt containing material or molecule that we have in our body. Okay, so to celebrate the birthdays yesterday and today of these three gentlemen, let us burst a few hydrogen balloons. Excuse me. All right, let's do it once more. So what we did was to ignite balloons filled with hydrogen, and the chemical reaction is one of the most fundamental reactions in chemistry, is 2H2 plus O2 giving 2H2O. So this is what we did, but I'm going to come up with certain questions to ask the students, and you can answer that in the chat box later on. We can review it at the end. So the question here is that assume that there were 5 balloons and the total volume was about 11.2 liters. So after we burnt it, it produced steam. But if we condense the steam, how much liquid water by volume will we get? Okay. So this is my first question, and there is one more question that is going to come up. But in this context, I would like to highlight the importance of asking questions. Most of the children at your age are probably taking a number of coaching classes for the competitive exams, and in many of these coaching classes, you learn how to answer questions and not necessarily to ask questions. But in science, the greatest understanding of science, and if not other subjects, come by asking questions, and often the right questions. Let me give you an example from a physicist. This physicist talked about his childhood, and he said that his mother made him a scientist without ever intending to. Because every other mother would ask a child after school, did you learn anything today? Or what did you learn? You may recall your younger days when whoever is at home, maybe your grandparents, maybe your mother, would typically ask you, what did you learn today? But he goes on to say, his mother would always ask him, did you ask a good question, Izzy? And then he says that difference, asking a good question, made him become a scientist. And who is he? His name is I. Rabi. He got the Nobel Prize in Physics in 1944 for discovering his resonance method for recording the magnetic properties of atomic nuclei. So basically what he discovered, a phenomenon called nuclear magnetic resonance. Many of you may not have heard of NMR, but you have heard about MRI. MRI, the magnetic resonance imaging technique, is basically using principles discovered by I. Rabi. So I'm going to ask you my second question. This is not the second question. This is something everybody knows. All of you who have studied history, have been to Delhi, would know what it is. But I will show you a tower which looks very similar to this. All right, take a look at it. This, in fact, is a chemical reactor. And I have already given you a hint about it. Towards the end of my talk, I'm going to ask you whether you have found an answer to this. If not, I will give you an answer. All right. Typically, when I give this talk, I do a lot of live experiments, which I am not able to do. So today, I'm going to show you certain experiments either through pictures or through videos. So the first one is through picture. Chemistry often looks like magic. For example, here's a magic experiment I'm going to do. So my students are holding a banner which has nothing written on it. And as you know, that cannot be true. And then here I am with a sprayer which contains a yellowish or brownish liquid. So I'm going to spray this liquid on this paper and some message will come out. Okay. I'm not going to show the same one. I will show a different picture. And here you see chemistry is fun came out after spraying the brown liquid on a white sheet of paper, supposedly without anything. But as you know that nothing can come out of anything. And indeed, you find that two types of colors are produced. One is deep blue and one is purple. One is deep brown. And this is because of different chemicals with which these letters were written. And most of the class 12 students probably would know what it is. Let me show you the chemistry behind it. So what I had in my hand was a solution of iron chloride or ferric chloride. The letters which turned deep blue were written with potassium ferrocyanide, these to combine to produce what is called Prussian blue, whose molecular formula is shown here. The letters which turned deep brown were written with potassium thiocyanate, and upon spraying with iron chloride, they produced a material, a complex of iron, which has a blood red color. So this is very simple chemistry, but it almost looks like a magic. I will show one more experiment. And this experiment is about heavy water. Most of you have heard about heavy water, which is nothing but D2O. Hydrogen is replaced by deuterium, the heavier isotope of hydrogen, and that produces D2O, which is called heavy water. It's called heavy water because it has a density which is higher than that of water. You also notice that D2O melts closer to 4 degrees as opposed to water, which freezes or melts at 0 degrees. Now, I would like to ask you a question. Well, I'm not going to wait for the answer in this case. Here I am. I'm holding 2 plastic syringes. One contains H2O, the other one contains D2O, and they have different colors. Now, I don't know which one is which. So my question to you in a real experiment, in an in-person meeting would be, can you tell me which one is which? So here it is online, so I will not wait for the answer because it will take time. So what I'm going to do is the following. It turns out, and as you all know, that H2O ice, whichever be the H2O, H2O ice is lighter than H2O. So ice floats on water. Similarly, if I make D2O ice, it will float on D2O. But then it turns out that D2O ice is very slightly heavier than H2O. Therefore, if I take a glass of water, cold water, and drop a D2O ice and an H2O ice, one will float, the other one will sink. And that's exactly what you see on the right-hand side. Here I'm holding a measuring cylinder containing ice cold water, and I have dropped these 2 pieces of ice. These are actually frozen samples. The orange one is floating on the top, but the green one has sunk to the bottom, therefore confirming that the green ice is indeed D2O ice. That's not all. If you wait for a few seconds, few minutes in fact, you will find that the D2O ice will partially melt. It will produce a green layer of D2O, and you will find that the remaining D2O ice is happily floating on the melted portion of the ice, that is the green D2O. So there is no surprise here. And the reason you do the experiment in ice cold water is that D2O ice, having a higher melting point, close to 4 degrees, will melt slower than the H2O ice, which is orange colored and floats on the top. So this is again a very simple experiment. If you have access to D2O, everyone can do this experiment, but I must point out that D2O is a bit expensive, but it can be done. Okay, so here I show a picture of the Earth with certain letters which are everywhere. And the reason I have drawn it this way is because it is chemistry, and chemistry is everywhere. Chemistry is often called the central subject. It is also a creative and useful subject. No matter what you think about, what you see around you is basically chemistry. So virtually every human activity uses some of the materials supplied or processed by chemistry. Even the mobile phone or the laptop that you are using to listen to this talk has materials which have been produced by chemists and material scientists. And of course, many such activities involve chemical changes. Just to give you an example of how much chemistry is there in, for example, in baking goods. Here I have taken the label from brown bread, commercially available brown bread, which lists on the back side a number of components that have gone into the production. These are, for example, emulsifiers, improvers, preservatives, acidity regulator, and antioxidants. And if you look at these numbers, these are called INS numbers, like International Numbering System of food additives, which are approved food additives. And I have listed all of them. I'm not going to discuss about any of them, but basically the first three are emulsifiers, which are used in making the dough. The next four are improvers of different types. And then, of course, you have a preservative, you have an acidity regulator, and you have an antioxidant. So the life of this finished product is improved better. So by looking at the labels and studying some of these numbers, the INS numbers of commercial products, apart from what you normally would look, that is the expiry date, if you do a little bit of reading and background study on these, you can learn a great deal of chemistry. Okay, as I said, chemistry is everywhere with the image of the earth, but I didn't quite mean that it is limited to the earth. And just to highlight that, I would like to take you away from earth and a picture that excited all of you, all of us, 8 to 80, or maybe 2 to 90 a few months ago. So this picture excited many of you because this is where the Mars Perseverance rover is being lowered on the Mars surface. And here's the rover, and here's the parachute, and here's a close-up picture of the rover being lowered on the Mars surface. Now, a lot of physics and a lot of engineering is responsible to take this rover from Earth safely down on the Mars surface. But you will be surprised when I show you the details of the actual rover and the equipment it carries. It in fact carries out a large number of chemistry experiments. These are some of the equipments that this rover carried, and the chemistry experiments and material experiments that each of these machines or instruments would do, for example, involve a lot of chemistry, production of carbon dioxide, production of oxygen from carbon dioxide, because the Mars atmosphere contains 95% CO2, a lot of mineralogy, detection and analysis of chemical elements, mineralogy and detection of organic compounds, and presence of organic compounds in rocks. And one of the main mission of this project is to find out if any biological molecules existed on Mars surface, whether there was life before, or whether there will be atmosphere that will support life in the future. And that will depend upon how efficiently this carbon dioxide could be converted to oxygen on Mars. I will show you a couple of other pictures. One is an older picture on the Mars surface, again, in the context of chemistry. Here you see July 1997. Again, a remote control vehicle is positioning a spectrometer against this Martian rock to do chemical analysis. Here's the result of chemical analysis. I will not go into the details. And here is another more impressive picture of the Titan, which is a moon of Saturn. This was in January 2005. Some of you may have heard about the Cassini mission, and it is the Cassini mission that dropped a probe called Huygens probe on the surface of Titan. And what I would like to highlight to you is that at the center of the Huygens probe is a chemistry instrument. It's a chemical instrument called GCMS, which basically analyzes the air, analyzed the atmosphere of Titan as the probe descended and crashed on the surface of Titan. And therefore, while, as I said, that we all get excited by these planetary missions, but remember that one of the major goals of these planetary missions is to do chemistry on a planet or a moon or a comet's surface. And I would, at some point of time, love to do this experiment, for example, on the Mars surface. And if you think that I'm only joking, I would like to show you that I have a boarding pass to Mars, and the scheduled departure is less than 5 years from now in July 2016. Okay, jokes apart, let's now have some chemical fun. And I would like to show a few experiments which will teach you certain principles of chemistry. The first one, well, actually it's not an elephant, but some of the students have seen this experiment. It's called elephant toothpaste experiment. It is in fact an experiment on catalysis. And I'm sure that many of you have heard about catalysis. And this catalysis involves decomposition of hydrogen peroxide into water and oxygen. This reaction does not happen unless you catalyze it, unless you heat hydrogen peroxide, which is in fact dangerous because it can explode. I should also mention to you that some of the hand sanitizers that you have been using during the last few years, they contain a very small quantity of hydrogen peroxide, about 0.125%. But that is a different issue. But what we are going to do today is to add sodium iodide to hydrogen peroxide and see how efficiently it catalyzes its decomposition. And to make the reaction a little more interesting and entertaining, we will add some liquid soap we will mix some liquid soap with hydrogen peroxide. And then when we turn on the reaction by adding the catalyst, the liberating oxygen will produce foam and it will come out as a toothpaste. So let's take a look at the video. I will shut down the video's sound and advance quickly to 1 minute and 20 seconds, where in this measuring cylinder on the middle left, I'm going to add hydrogen peroxide, sodium iodide. And you see oxygen starts evolving. It comes out as a foam, and this is the so-called elephant toothpaste experiment. And the fact that you are producing oxygen here also liberates a lot of heat. You can see some steam coming out of it. It's a very messy experiment, produces a lot of foam, and you see this foam keeps coming. And I would like to give you a proof that it is oxygen by lighting a matchstick, and that will be at 2 minutes and 20 seconds. Let me advance it to there. And you know oxygen supports combustion. So we will put a matchstick there in the foam and you will see how it glows up. Okay, so you see the glow, that means it is supporting the combustion of the already extinguished or partially extinguished matchstick. So this was the experiment on catalysis. I hope someday I can show it in person, but not today. The second experiment I'm going to show you is a reaction which is called an oscillating reaction. Most of you probably have not heard about it before. It's called Belousov-Zhabotinsky reaction, discovered by these two Russian chemists many decades ago. And in this reaction, unlike what you normally do is write down a reaction and it goes from left to right. But in this case, it goes from left to right, all right. But then again from right, it goes back to the left. And this cycle continues a few times. Let's watch it. This was done during an open day. So you see a lot of background sound of the visitors. So you see this color appears, disappears, appears, disappears, and so on and so forth. The theory for this is very, very complex. The second one that I'm going to show right away is a reaction where you ignite a solid by touching with a piece of ice. Magic? No, there's no magic. In fact, the reaction is catalyzed by a drop of water. And by touching it with a piece of ice, you just make it look dramatic. But actually what you are doing is to provide a small drop of water to a mixture of a few chemicals, which I will not disclose because it's quite dangerous to do this experiment. And what you will see is that the reaction will generate so much of smoke and heat. Because of the heat, the porcelain vessel will crack and burst into fire. Okay, let's watch this reaction. You will not be able to see touching it with the ice part. Once more. Okay, so this is igniting a solid supposedly by touching it with a piece of ice. Again, a magician can do it and not tell you the chemistry behind it. Now, a little bit about chemical bonding, because after all, as I said in the first slide, chemistry is all about making and breaking bonds. Now, most of the students may be familiar with this kind of a diagram where I show the orbitals on two atoms which are combining to produce bonds. This is the simplest way to look at it. But if their sizes are unequal, like trying to shake hand with a small baby, the handshake will not be physically strong. And that's what happens when you try to bond atoms which have very dissimilar sizes, like a nitrogen with a chlorine or a nitrogen with an iodine. Ni bond strength is only 40 kilocalories per mole. Okay, I'll show you one which is very strong. For example, when orbitals or the hands are of comparable sizes, you get a firm handshake and a strong bond, like a carbon-carbon bond, carbon-fluorine bond, or carbon-oxygen bond. And you can easily see that the energy is double of this. Incidentally, 40 kilocalories is about 10 grams of sugar or 2 spoons of sugar. So while I'm talking about chemistry and bonds, I am also trying to correlate it with some real life examples. So 40 kilocalories is 10 grams or 2 spoons of sugar. Now, one Ni bond is weak. A weak bond essentially means it is packed with energy. Why do people make that? Because such molecules make good explosives. Of course, explosives can be used for both good and bad use. Now, I'm going to make now all the 3 bonds to the nitrogen with iodide. Imagine a small nitrogen surrounded by 3 huge iodine atoms and 3 very, very weak bonds. And what happens is that makes this material Ni3, very simple material, brownish, dark colored solid, but it is extremely, extremely sensitive to touch. So let me show you a video. I have to go back.
When nitrogen triiodide, the dark-colored solid, is dry, it is very sensitive to touch or any vibration. Simply touching it with a feather causes it to explode or detonate. One detonation causes another to occur. One product of the reaction is violet iodide vapor.
I hope you are able to see that by touching it with a feather, it exploded. And here comes question 3. Question 3 is, if it is so shock sensitive, how do you put it on the filter paper in the first place? Answer in the chat box. All right, now these are bonds which are some strong, some weak, but let's go to bonds which are even weaker. For example, hydrogen bonds. Hydrogen bonds are bonds between a bond with a hydrogen which is shared by 2 electronegative atoms, X and Y. You may ask that, why do we study hydrogen bonds? Hydrogen bonds are important because they give a particular structure to the building blocks of our life-giving molecules. On the left-hand side, you see the alpha helical structure of a protein, which was discovered by Linus Pauling. And I will tell you the story towards the end of my presentation if there is time. So this is the alpha helix of a peptide, which is held together by hydrogen bonds between one turn of the helix and the other turn. And the other one, which again, all of you know, is the double helical structure of DNA, where there's a hydrogen bond between A and T and G and C. Hydrogen bond is also something that makes life possible for a different reason. If there was no hydrogen bond, H2O would have been a gas, but it's not because of strong hydrogen bonds in liquid water. But it turns out that in solid water, that is in ice, there are fewer hydrogen bonds. Let me show you, this is the structure of ice. You see that there are a lot of open spaces here. And on the lower left-hand side, I will show you an animation of liquid water, which is being frozen. Let's see if the animation works. Yes, this is liquid water, very condensed, a lot of hydrogen bonds, but when it starts to freeze, it opens up. So the volume is larger and therefore the density is lower. Now, I would like to show you an experiment on what happens when water freezes. This is something you have done on your own by putting a plastic bottle full of water in the deep freezer. And what we're going to do is a bit extreme.
The ice bomb illustrates the fact that the volume of ice is greater than the volume of an equal mass of liquid water. Some cold water is poured into a cast iron bomb, and a threaded plug is screwed into the bomb so that the bomb is tightly sealed. The bomb is then placed into a dry ice acetone slush, which is at negative 77 degrees Celsius, and will cause the water inside the bomb to freeze. A wooden box is placed over the top of the bomb and slush bath. It takes a short time for the water to freeze. When it does, the bomb explodes. Some of the dry ice acetone slush is blown onto the explosion shield. Little bits of the cast iron bomb are left. When the water freezes, tremendous pressure is produced. The pressure is enough to cause this cast iron bomb with more than 1/8 inch thick sides to burst.
So therefore, what you have just observed is that when water expands, if you confine the space by putting everything in a strong iron container, it can generate so much force that the iron container may explode. So again, the effect of losing a very large number of liquid water when it freezes, because in solid ice, the number of hydrogen bonds are fewer. Okay, so that's for small and weak bonds. What about strong bonds? For example, the bond in carbon dioxide. You know, there's a lot of talk about CO2 because it is a greenhouse gas. We are producing lots and lots of CO2. So there is a lot of active research that is going on in chemistry all over the world to find ways of converting carbon dioxide back to a fuel. This, of course, would require energy. So until we find a sustainable way of doing it, it will not be successful. But let me show you by doing a non-sustainable chemistry, how you can at least break a CO bond. So this is the strength of a carbon-oxygen double bond. And this experiment involves burning magnesium and carbon dioxide. And again, it's on a video. This uses the carbon dioxide we are going to use will be in the form of dry ice blocks. So let's watch this video also.
Magnesium is placed in a cavity in a block of dry ice. The magnesium is ignited.
So you ignite the magnesium and cover with another piece of dry ice.
And covered with another block of dry ice.
So the burning magnesium has no air, no oxygen, only carbon dioxide. But watch what happens.
Despite the absence of air, the magnesium continues to glow due to its reaction with carbon dioxide. Because of this reaction, carbon dioxide cannot be used to extinguish magnesium fires.
So that's another lesson, that metal fires cannot be extinguished by carbon dioxide because the metal will continue to burn in carbon dioxide. Most alkaline earth metals. Let's see what's inside.
The reaction products are white magnesium oxide and black carbon.
You can probably write a balanced equation because in the video you heard that the products are white magnesium oxide and black carbon. So what magnesium has actually done is to extract the oxygen out of carbon dioxide and reduce it to black carbon. This is not sustainable because magnesium does not occur free in nature. And to convert magnesium ore into magnesium costs a lot of energy. What about breaking nitrogen-nitrogen triple bond? And that has an energy of 227 kilocalories per mole, one of the strongest bonds that you find in natural materials. So we'll again come back and address this question later on. The next few slides, I will show experiments with color. The first one is about change of color with solvent polarity. You all are aware of liquids of different polarities. For example, water is a very polar solvent. It dissolves things like salt and sugar, whereas petrol is a non-polar solvent, and that will dissolve non-polar compounds such as naphthalene. I'm giving you examples of materials which are found in any household. But there is one particular dye, an organic molecule, a synthetic molecule called Reichardt's dye, which has a unique property of showing very different colors in solvents which vary very little in their solvent polarity. For example, here is the chemical structure of the molecule. I will not go into the details here, but this is methyl alcohol, ethyl alcohol, isopropanol, acetone, and anisole. And you see very distinct colors. As you are aware that many poor Indians die because of methanol instead of ethanol. Some of the cheaper drinks, they make use of methanol. And would it not be nice to find a quick way to distinguish methyl and ethyl alcohol? And this dye actually allows you to do that. You see very distinct colors. And isopropanol, excuse me, which is also a common solvent used in many applications, again gives a very distinct color. I will show you one more panel to sort of broaden the list of coloration, and that is here. And you see that in dioxane, chloroform, acetone, going all the way to methanol, you see very distinct colors. So this molecule has the world record of showing the largest difference in color in solvents of different polarities. In water, it is not soluble, and that's why you don't see any color here. Okay, the next example I'm going to show is on thermochromism. And thermochromism is change of color with temperature. And here's an example of a magic glass that I have. It's not magic. I'll tell you the reason for it. And let me show you a video taken in our lab where you will see ice cold water is poured into the glass, and then we will mix it with some ice at the top and stir it. And you will see that the color changes. And ultimately, the entire glass becomes red. It is because there is a thermochromic chemical embedded in this plastic. And now the entire glass became red because the temperature dropped below 5 degrees. So we will take this glass, pour the water out, and now, so that's how it looks. It is still cold. But when we add some more liquid water, which is at a higher temperature, you see that it has warmed up the lower part of the glass, and that has now become the same original color. So it's a reversible change of color, and there are many thermochromic materials, and many of them are very useful. For example, if there's a pipe in a factory that carries a hot liquid, which you are not supposed to touch, you can write hot with a thermochromic material, which will show a red color, such as this. And chemists can design such molecules which will have a predictable color change at a predictable temperature range. This picture was taken a few years ago when life was still normal and one could travel without worrying about any infection. What you see is the blue sky and the red sunset from an aircraft. Now, all of you know that this is a physics phenomenon because of scattering of light, and both phenomena can be explained by scattering of light. So what I'm going to show you here is in fact a physics experiment, but there is some chemistry factoring built into it. And generally speaking, when light passes through a medium, and medium means it has gas, liquid, or a solid, it can be transmitted, it can be scattered, or it can be absorbed. If it is absorbed, then it can be subsequently lost as heat, emitted at light of lower energy, that is longer wavelength, or it can undergo a chemical reaction. So light absorption followed by chemical reaction is an active area of research, and that is called photochemistry. But today I'm going to show a simple experiment, again with pictures, where you will see scattering of light and fluorescence. So this is what we are going to do in fluorescence. We will shine green light and get yellow-orange light output. And for doing this experiment, all you need are two laser pointers. One is red, one is green. But there's a warning sign here. Please take a look. It will go away in a second. I will wait for a minute, wait for a few seconds. And the other things that you require for doing this experiment are a drop of milk added to some water. It need not be a measuring cylinder. It can be glass. And in the other container, you take water and you stir the tip of a pink highlighter pen. The pink highlighter pen contains a dye called solvent red 49. Again, details are not very important. So what we're going to do is that this will show scattering. So the first thing we're going to do is to shine the red light through it. You know, if it were plain pure water, you will not see the light beam because clear water is colorless. That implies that it doesn't absorb any visible light. But you are seeing the light beam and you are seeing the scattered light because of the milk droplets, milk particles scattered all over the, distributed all over the liquid. And you do the same thing with the green laser. Again, you see scattering of the green light. And that is, again, as I said, red light is scattered, green light is scattered. Now we do the experiment with this solution, the pink solution that came out of the pink highlighter pen. With the red light, again, you see scattering. The dye alone would not show any scattering, but as you see, the solution looks a little cloudy because the pen, the tip of the pen has not only the dye, but also things like silica, which allows the spreading of the ink on a paper surface. So that is also scattering. But when we shine the green light through this one, things change because this dye absorbs green light and re-emits as fluorescence in the yellow range. And that's exactly what you see here. And you notice the difference between the top image where you see scattering of green light and here is absorption and emission of green light into yellow. If you are not convinced or if you still don't believe, I will show you a quick video where we tilt the laser at the top and you will see the yellow light and its reflection on the back. Okay, I hope that will convince you. There's nothing like doing the experiment in real life, but as I said, that is a bit tricky to do it today. All right, the last experiment I'm going to do is about chemiluminescence. Again, color. So in this experiment, what is done is chemical energy is converted to light energy directly. Just what the fireflies and many other organisms do. And since such things happen in biological systems, it's collectively called bioluminescence. But today we are going to do a chemiluminescence experiment, just a little bit of chemistry so that the students are aware of what's happening. We come back to our old friend carbon dioxide, but we make carbon dioxide and hydrogen peroxide. So we mix these two chemicals. This is oxalyl chloride, and this is our fuel, hydrogen peroxide, to make what looks like a CO2 on the top and the CO2 carbon dioxide on the bottom. Now, if I don't do anything, this molecule is very unstable. It will split into two carbon dioxide. One is black carbon dioxide, which is like our everyday carbon dioxide that we inhale or breathe out. This carbon dioxide, the red one, has the extra energy. Where did the extra energy come from? It is because of this weak OO bond and breakage of the strained ring size. Again, if I don't do anything, this extra energy will be lost as heat. And that everybody knows. You can convert chemical energy into heat energy. And that's not fun. So the fun part comes if I add some other acceptors which can trap the energy from the carbon dioxide and itself contains the energy. So CO2 star has transferred the energy to A, and now A has become A star. And if I now choose the A star molecules carefully, I can get a photon or a light out of it. And by choosing different A molecules, we will get lights of different frequencies and therefore different colors. So there are 4 dyes we are going to use today. Again, the names are not very important. The first one will give you a blue-violet color. Second one will show you an orange color. The third one, a sky blue or a cyan color. And the fourth one, a green color. And these are 4 different molecules giving 4 different colors. And again, I will show you a video. And I will go to 55 seconds. Let me go to 55 seconds. Oops, sorry. Yeah, let me start here. So this is sky blue. Now this is blue violet, and this will give you orange color. So I'm adding the fuel hydrogen peroxide. This is 9,10-diphenylanthracene. This is rubrene, and you will see me shaking this to flasks. Beautiful bluish violet color and beautiful orange color. And now I will go to 55 seconds to show you the second part of the experiment, to show the cyan color here and the green color here. Okay, again, I will shake this to flasks. There is nothing like doing this experiment, in a completely dark room. You can actually see my face if I bring this to flasks close to my face. And now I would also like to compare the two different blue colors. As I said, these are two different chemicals, and they give lights of different colors. So this is a very simple experiment on chemiluminescence. Now I see that my time is reducing. I have another 10 minutes to go. And here's a picture of all the four colors that you see. This is from diphenylanthracene, rubrene, arylene, and tetracene, the four different colors that you see. And here is another picture of the blue, violet, and the orange color. And it turns out, if I mix them in the proper proportion, in the mixture, I will first have an orange color, which becomes white, and then eventually it becomes blue again. And that's a very fascinating experiment to do. And hopefully someday I can show these experiments in person. So that's the end of my presentation as far as the slides are, as far as the experiments are concerned. But coming back to this question of what is this? Was there any answer on the chat box?
I don't see any answer to that.
All right. You remember I talked about the Haber-Bosch process for making ammonia? It turns out that this was one of the first ammonia reactors made by Haber. And this is kept as a monument outside the largest chemical factory of BASF in a place called Ludwigshafen in Germany. And this tower, or this reactor, produced about 800,000 metric tons of ammonia over 55 years. And as I'm sure all of you know, that ammonia is a very useful nitrogenous starting material for making fertilizers. Okay. So the next thing that I would like to do is to come back to this alpha helix structure and remember Linus Pauling, who developed the model for the alpha helix. Linus Pauling is also the only person who got two unshared Nobel Prizes, one in chemistry, one in peace. I have a slightly longer video on his life, but I will not play that. But in this video, he talks about his discovery of the alpha helix, which he did when he was in a hospital bed in Oxford. And also for 11 years, he tried to solve the structure and he was not successful. So therefore, my message in this context to the students is that even if you are not successful today, don't give up and try it again. So even Pauling discovered alpha helix from a hospital bed. But don't try alpha helix because it is already done. So therefore, never give up, even when you are in a difficult situation, such as what you see on this cartoon. Another point I would like to highlight here, imagine a situation such as this, that your door to the entry of your house is sitting over an open drain and whose cover is missing. Now, in this case, you cannot afford to make a mistake and drop your key. You will not be able to get in, right? So there are certain situations such as this where failure is not an option. So that's what I would like to highlight to you by showing you this little message from Apollo 13. If you do not know in what context these words were said, you should look up Apollo 13 mission and you just put the entire phrase, failure is not an option, within quotes and search for it. And you will find out the absolutely fantastic mission which failed. Apollo 13 failed before it reached moon. but NASA said failure is not an option. We will bring back the astronauts, and which they did. So one more thing I would like to tell you before I close, and that is always keep your eyes open. Another way of saying it from a famous person is chance favors the prepared mind. You know, nature presents to you many types of problems, many types of opportunities in front of you. But if your eyes are closed, by saying keep your eyes open, I don't mean that eyes have to be physically open, but your mind should be ready to explore and exploit a chance that nature presents before you. And if you don't do it, somebody else will do it and get all the credit. Before I close, you know, periodic table is one of the most important tables for chemists. And perhaps many of you are aware that it was first published by Mendeleev in 1869. So 2 years ago, 2019, was the International Year of the Periodic Table. And since Professor Tirthankar Bhattacharya is here, I would like to show you that mathematics and chemistry can go together. And here is a periodic table song which was composed and sung by a mathematics professor of Harvard University. And you will hear, his name was Tom Lehrer. This song was composed sometime in the 1950s or mid-1950s, but there are many versions of it with animation, without animation on the web. But in the time that I have, I will play the song from Tom Lehrer in a program in Copenhagen, and you will hear him singing his periodic table song.
Now, here's a song I always get requests for, but I can't understand for the life of me why. It's simply the names of the chemical elements set to a Gilbert and Sullivan tune. I think the only reason I do it is to see if I still can. We'll try it. There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, actinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. Citrium, terbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, lithium, beryllium, and barium. I left that one, actually. A new one was discovered since the song was written. It's called Laurentium. So those of you who are taking notes can write it down in your programs. There's holmium and helium and hafnium and erbium, phosphorus and francium, fluorine and terbium, manganese and mercantile and lithium, magnesium, viscosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium, tantalum, lutetium, titanium, tellurium, and cadmium and calcium and chromium and curium. There's gold and californium and fermium, berkelium, and also mendelevium, titanium, nobelium, and argentinium, radium, rhodium, and chloride, copper, tungsten, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Okay, there is a little bit more in the video, but I stop because my time is really running out. I do hope that you have enjoyed the last 1 hour of discussion of chemistry through experiments. The way chemistry is put together in a high school syllabus is actually very obsolete. And I think the teachers also find it difficult to teach in an attractive way. But I think you can make use of some fun out of chemistry at all times. But more than anything else, I hope that you would find chemistry less boring and more enjoyable now that I have shown you some ideas, and you can expand on some of the thoughts that I've given to you. These are newer experiments. And one thing to keep in mind, whenever you do chemistry experiments, take safety precautions at all levels, and must make sure that every element, every material that you're using for experiments is safe to handle, and you're using proper operating procedures. So with this, I would like to close. Before I close, I would like to give again the same message to all the students that stay safe, wear masks, avoid crowded places, and maintain physical distancing. With this, I would like to thank all of you for your patient hearing. Thank you very much. I'll stop sharing now.
Thank you for a very informative and entertaining talk.
Thank you.
Will you take some questions?
Absolutely. Okay, we
starts with Oshnik Nath.
Yes, we have a very young friend. I think kilocalories per mole, I will explain to him privately. This is a unit of energy. Just like sugar gives you energy, 1 spoon of sugar, as I said, is 5 grams of sugar. It gives you a certain amount of energy, which is one spoon of sugar will give you about 5 times 4, that is 20 kilocalories per mole, 20 kilocalories. And 1 mole is the Avogadro number of molecules. So this energy comes from that many molecules. So 1 mole will give X amount of kilocalories. But just to give you an idea, 1 spoon of sugar gives you 20 calories. And for an adult human being, you need about 2,000 kilocalories per day. That's our diet requirement. Okay, there's a question from Maitreyi. In the explosion experiment where the feather ignites the component, I think the compound is synthesized on the layer itself. Is that correct? Yeah, I asked the question that if it is so shock sensitive, how do you keep it on the filter paper? Your answer is almost correct, in the sense that when you make it as a water slurry in water, and water takes away all this shock sensitivity. Just like, gunpowder, if it is wet, it will not explode. So you keep the wet material on the filter paper and run away from it to dry up. So I think my young friend has some comments here. Oshnik, molecules of salt and sugar bonds with the water molecules to add more sugar or salt. We need to heat the water, and this process is called supersaturation. All right, very good. There is another question from Srihari. Why is periodic table manipulated for helium? Well, I won't say it is manipulated. Periodic table has gone through many changes because, as you know, perhaps that when Mendeleev came up with the first version of the periodic table, there were hardly 65 odd elements. And his genius was to keep vacant places in certain places. He didn't pack all of them and made the table. He, based on the properties, he arranged things and kept blank spaces. And surprisingly, I mean, not too surprisingly, a few years after he generated the periodic table, those blank spaces were filled up by new discoveries. And that really made Mendeleev a superstar. So similarly, the position of hydrogen, the position of the inert gases were not known at the time of Mendeleev. They were all discovered towards the end of the 19th century, 20th century, 19th century. And therefore, those places were modified once we understood what is the most fundamental property in elements, and that is the number of protons and not the atomic weight. Okay, I think there are not additional questions. I think it looks like we are done.
All right.
Thank you.
So then I would like to thank all the speakers as well as Professor Partha Mujumdar, whose initiative was this, and Ma'am Madhugaur. They are the ones who actually corresponded among themselves and conceptualized this. So many thanks to them, to the Indian Academy of Sciences, to the Academic Trust, and to the DAV Centenary School, Narela, for this exciting series of lectures on 4 basic sciences. I think we would close this session.
Thank you.
Thanks to all the participants as well. Thank you.